whenever you want. Qurat, the floor is yours. Thank you very much.
Thank you. Good afternoon, everyone. I'm Qurat from University of York, and today I'm going to present our work on efficient model comparison using automated program rewriting. This work is done in collaboration with my supervisors, Professor Dimitris Kolovos and Konstantinos Barmpis. So today I'm going to start with introduction, so a little bit about a few terms that I would be using during this presentation. Then I'll touch upon the tools and technologies involved in the context of this research, which is Epsilon, and in particular ECL, Epsilon's comparison language. I'll talk a bit about the problem statement and the motivation behind this work. Then I'll talk you to the proposed approach step by step. And finally, I'll share some results of our approach, and I'll conclude with a summary and some future directions for our work. So, because models, I know this is a session on modeling, but models can be used in the machine learning terms as well. So I just thought to give a brief overview of what I mean by models here is, so models are basically an abstraction of a real-world system, which is for a given purpose. And then in model-driven engineering, models are the first-class citizens, so they are the primary artifacts from which we generate other software artifacts. So we have various model management languages to do various model management tasks. So we can actually generate code, transform models, compare them, merge them, etc. So in the context of this talk, we are focusing on model comparison. So I'll just say a few words about what model comparison means. So model comparison means to establish the correspondences between two models that you're comparing. And model comparison is usually a prerequisite for other model management activities, such as model differencing. So if you want to calculate the difference between two models, it is important to identify the matching pairs. Similarly, for merging, to not have duplicates in the merged models, it's important that you identify the corresponding matching elements. So now we know what is model comparison. What are the ways to compare models? So traditionally, we can use the traditional text-based comparison, or unique identifiers. These are simpler, but they provide limited support, and they cannot be applied to heterogeneous models. So we have a dedicated rule-based language, which is Epsilon's comparison language, that allows you to have a precise matching algorithm that can be specified by the developer to have a custom matching logic. So just a depiction of what model comparison looks like. So if you see, we have a object-oriented model, a relational model. So we put these two as an input, and they correspond to their corresponding meta model. And then the model comparison task will yield a match trace. And what is a match trace? It's nothing but a table that looks like this. So we have a left elements, like this one, and we have right elements, and then we have a Boolean flag that basically shows if these elements match or not. So before I go to ECL, I think it's important that I say a few words about Epsilon. So Epsilon is a family of model management languages, and it provides an abstraction to different modeling technologies using this model connectivity layer, where you can access different models, and then you can use any of the language depending on the task that you're targeting. So the main thing to take from here is that Epsilon's main core language is EOL, Epsilon's object language, and all the other languages are built on the top of it. So the language of interest here is ECL, which is used for model comparison, as I mentioned. Now, before I go to proposed approach, like how ECL looks like. So ECL is, as I mentioned before, is a rule-based model comparison language. We can compare two models from the same modeling technology or from different. And then an ECL program looks like this. So if you see, we have a we have a rule here saying tree to tree. Basically, what this rule is doing is comparing two tree models conforming to this meta model. We have a keyword match that specifies one model element and then the other model element to compare it with. So L is a model T1, and then R is a model T2. And then what we do is we have a compare block which specifies the matching logic. So what's happening here is we're checking if the label of tree is similar and the parent of the left tree is the same as the parent of the right tree, and also the same for the children. The important thing here is this matches operation, because this is just an equal operation. This matches operation is basically a built-in operation that ECL provides, and this is basically used to avoid duplicates. So basically, this provides decoupling of rules. So for instance, this matches operation calculates the model elements compared by the other rules. In this case, there is just one rule, so this matches will call the same rule again. So this is what ECL looks like, and ECL also has can have pre and post blocks. So pre blocks will be statements executed before the match rules, and post block will have statements to be executed after the match rules. The output of an ECL program is a match trace which contains several matches of left, right, and a Boolean flag. Right? So now we've seen what ECL looks like. The problem here is that when we are in an industrial setting, or we are dealing with enterprise applications, the size of models is usually quite big. So we have models ranging from millions of elements. So we need to make them scalable to make more efficient use of the resources, right? So as I mentioned, these languages like ECL, they are tailored model management languages. So they are specific to the task that they are targeting. They're simpler to use, but because they are interpreted, most of the time performance becomes an issue. So especially in model comparison, where we have to traverse every element and compare it to the corresponding element of the other model. So I think a motivating example will help understand better what I mean by this. So for instance, we have a sequence diagram here, a meta model of a sequence diagram, a meta model of class diagram here. And suppose we want to compare models conforming to these two meta models. So we have an ECL program written here, a very simple one. We're comparing message to operation. So we're checking if the message and operation name are same, and they belong to the same class, right? And then we're comparing lifeline to classes. But if we want to evaluate this on these small models, so this is a small class diagram, a small sequence diagram, the match trace that we will end up with would be this. It's a huge match trace for just some small models. So imagine if we are considering the underlying models to be in order of millions of elements, then we'll end up with a huge match trace, which will decrease the performance of ECL engine. So the idea is to optimize the ECL program so that we can end up with a filtered or reduced match trace, right? So the approach that we have proposed for this is illustrated here. I will go through this step by step, but the main idea is this, that we have a ECL comparison script here that is comparing a left and the right model conforming to their respective meta models. And then we have a static analyzer block that takes in the abstract syntax tree. Here we have a, if you remember the diagram that I showed you earlier about epsilon, because ECL extends EOL, so the static analyzer also extends the static analyzer of EOL. So what will end up from the static analyzer block is a type-resolved AST, which would be the same AST as we've seen here, but with the type information attached to it. Then we would use a dependency graph generator that would generate a graph that will depict the dependencies between various match rules. And then that would help us for the scheduling of rules. In parallel, we have a optimizable rule detector, so we'll detect which rules we can optimize. And then there is a rewriter that rewrites the whole comparison program. So now this comparison script is reduced to this rewritten comparison, and this will be executed on the ECL, the traditional ECL engine that is available. And what we'll end up with is a reduced pre-filtered match trace. So that's the whole idea. Now we'll just look at each block one by one. So the static analyzer block. So the same program that I've shown you in the motivating example. So what we do here is static analyzer basically computes types of the various constructs. So as an example, the L variable here, because the type is specified to be a message type, which is a EOL model element, and then we would have the same with the operation. It's a model element type, so on and so forth. And suppose for the primitive types, r.name, as shown from the meta model, is a string type. So this is what static analyzer does. So now we have a AST, which has all the type information attached to it. So in the second phase, where we have a dependency graph generator, what happens is these matches operation. Basically, this matches operation has means that it is dependent on another rule. So the resultant of match flag of the other rules needs to be attached here. So what we do is we compute based on the types that we've resolved from the static analysis. We see which rules are dependent on which. So for instance, if you see L.2 here, 2 is a type of lifeline from message, and then R.class is a type of class here, and then we know that this is calling a rule lifeline to class, any rule that is comparing lifeline with class. So the dependency graph would end up like this. So we'll know that message to operation rule is dependent on lifeline to class rule. So that's what dependency graph generator does. In the second bit, we have a rule scheduler. So rule scheduler takes in the input from the dependency graph generator and schedule the rule accordingly. So for instance, here, this lifeline to class rule is independent, and message to operation rule is dependent on this rule. So the rewritten program would put the second rule at the top and the message to operation one below it, because when we would ask for this matches operation, the result would also be would already be calculated by this rule, right? So the idea is to use the input of the dependency graph and use it to schedule the rules. Now we will come to the second part, which is the detection of optimizable rules. So here what we do is we basically find out expressions like this. So expressions where we are comparing using an equal operator. So now we know that we only need to compare those lifeline to classes where the name is similar. So what it currently what it will do is it will compare all the lifelines with all the classes. But if we know this beforehand, we can index this, right? So before going forward, so from after this step, what we will end up with is the rule and this field from which we need to create an index. So the second step in the rewriting phase is injecting caches. So I mentioned about the pre-block usage in the epsilon's comparison language. So we have a mapped by built-in operation provided by EOL. So what we do is we are creating an index based on the name field. Why we're creating it on the name field? Because we're comparing the name field with each other here. So now we've created an index. We need to rewrite the program. So this program, if you see this program, it will be rewritten to this. Now there is this thing which is different. So what we are doing is we are creating a concept of domain. So we've extended ECL to include this keyword from. It will filter this R array, and it will just compare the ones which have the same name. So L.type would return the name of the lifeline, and then this class map is a index that we've generated here. So in the compare block, we're just writing true. So it will only compare the lifelines with the classes. So this is a simple example of the rewritten script. And then when we execute this script over the ECL engine, what will happen is we will end up with this match trace. So if you see, this match trace is much more smaller than this huge match trace that we ended up without an optimization algorithm behind the ECL script. So this is the proposed approach. Now we evaluated our approach with the two types of models, so class and sequence diagram models that we mined from GitHub, and then synthetic models of object-oriented and DB. And then because we are rewriting the program, it's very, very important to ensure that the program is still correct. It produces the same output as it should be producing before the optimization. So we did it using the equivalence testing. I'll talk a bit about it in the next slides. And then, like to compare our results, we use the traditional ECL engine, which is the one that ECL normally does. And then we have rewritten the script using the optimization algorithm that I just showed you, and then executed it using the same ECL engine to see the comparison between the results. So here, the graph that you can see is a graph comparing class and sequence diagram models. So this blue line is for the traditional ECL, and this red line shows the optimized ECL. And you can see there is a huge difference in the execution time. Obviously, it comes at the cost of memory because we are storing a cache. And then same for the OO to DB example. The red line depicts the optimized ECL, and this one is the traditional ECL engine. This is the table that depicts the number of model elements that we've evaluated our approach on. So just the final bit about evaluation is here it's the equivalence testing that I was talking about. So we have, these are the number of matches basically. So we have number of all matches in ECL and number of all matches in optimized ECL. And then we have number of successful matches in ECL and then the optimized version. So what you can see here is that the successful matches number still remains the same, which is what we expect. But the all matches are reduced because now we are comparing a pre-filtered domain. So same goes for the class sequence diagram model. To conclude, I've talked about an approach which optimizes model comparison program using three main techniques: static analysis on the top of it, and then dependency graph, and then program rewriting. So we have experiments that deliver significant performance improvements in terms of execution time. So this is what it can do currently. This rule-based, because EPL is another epsilon-based language, epsilon pattern language, so these optimizations, like the dynamic domain concept, can also be integrated with other EPL language, and also we can include more experiments to show comparison between different modeling languages like Simulink and repository-based models. So in paper, you can find more details on the running example, and also you can find algorithm, how we identify optimizable rules and how we do the rewriting. That's it from my side. Thank you very much, and I'm open to any questions.
Thank you very much for the presentation. So is there any questions? We have many time for questions. Yeah, please.
Hello, thanks for a nice talk. So I was wondering, the result that you get is a match trace between matching objects. So is it trivial to produce a diff from this match trace and the original models? Or is that, would that be complex?
Sorry, can you repeat, is it trivial too?
So if I would like a diff between the models, is that easy to get from the match trace?
Right. So if you want to have a diff, matching is the first thing that you would do, like to identify which elements are matched. And then differencing is the second task that you would do on the top of it. Now you know which elements are matched. And these matches, remember, because these are on a custom matching level algorithm, so it depends what matching algorithm you write yourself using ECL, right? And then you would calculate a difference, because now you know that which elements correspond to each other according to your comparison language, logic. Yeah.
Okay, thank you.
Any other question? Yeah, Nico.
Yeah, also thank you for your talk from my side. I have one question regarding the optimization. Did you face some kind of rules which were, let's say, hard to optimize, where you couldn't gain anything?
Yeah, if I just go quickly back to the example, this is an equal operator. You could find rules where, you're just comparing based on the similarity and not equals. So you would not be able to optimize. Currently, it just works with the equals operator. So I think it's a very basic stage. So if rules get complex, or sometimes the logical operators here, if there is an OR, we cannot just optimize based on the first operand, right? So in that case, it's challenging, yeah.
Hello, very good. My question is, this is one model to model, like one model to another model, no?
Yeah.
So do you foresee, like, how would be the possibility to do multiple models at the same time? Specifically, for example, that you have a data set of models and you want to have a threshold of this amount of models, like these models here are similar to this particular one. At the same time, it will be too complex for the the execution time or something like that, or it's not that complex?
Basically, because you can specify a custom matching algorithm, so you can say one rule is comparing model elements from two models, say A and B, and the other matching rule can compare models elements from, say, C and D or C and B. So that's what the language can support. So in ECL, you can support multiple models, but obviously the result would be, how it would perform in terms of execution time is something that we have to see after the experimentation.
Cool. Any last question to Qurat? Yeah?
Thank you. Okay, thank you for the talk. You briefly mentioned that because of caching, you may have some problems with memory. I couldn't really see the scale for the last plots that you showed, but apparently you had really, really big models. Did you reach, what's the estimation you have for the memory that's used for these very big models? And if it's too high, is it actually usable for those very, very large models?
Yeah, it's a good question. Because I think when we were comparing using the normal ECL, we've reached the point where it was taking like 2 hours to compare two models. So we haven't reached to a level where it was like memory, full memory, but because of the time restriction, we couldn't like go to the higher models to basically compare, because for the normal ECL, it would go timeout. But because it's caching and it depends on how many rules are optimizable, it can reach to that level where, memory cannot take it anymore, yeah.
Okay, so thank you very much, Qurat, for the presentation and the nice answer. I think we can thank again Qurat and give her an applause.